Okay, so let's get started. So the last lecture. Yeah. So a bunch of correction from last lecture. There are lots of mistakes I made in the previous lectures. First of all, so what we considered last time is something like whatever. Entry level. So what we have in entry level, so we just have the correction of this factor. Correction to this factor, and then what we have shown is that the let's see. So if you include up, down, terms range, top and bottom, and we include this one. So therefore, what we have is indeed 3 times so it has to be minus 1/3 squared. The last time I written 2/3 here, but this is for bottom. Terms range up and down, and what you get is 4 pi alpha square. So alpha square 3s and 3, and you can calculate this is 9 over 4 plus 1 times 2 plus 1, and this is equal to so this is sigma 0, this is sigma 0. So therefore, this is indeed 5, 10, 11 over 3. So that's how we obtain the QCD 3 level E to hadron, E to the hadron. Okay. And the reason why you don't include top coke is top coke is very heavy. I already thought top coke, the mass of top coke is 100 something GB. So more than 100. So therefore, if you try to create a top coke in between, you have to have a correction to Z boson in fact. The Z boson QQ. So Z boson is lighter than top quark. So if you try to create top quark, then you have to also consider Z boson's correction. So you need to include this diagram so that the so we just do the experiment at the level that's at less than energy level, which is less than, and Z boson, which is around 90 Z. So that's one correction I want to make, and there are lots of mistakes. The last time, so when I sorry, this is not my stuff indeed. So what we consider is this diagram. So, and then I just take, when I mention dimensional regulation, I just take this limit. But the calculation I did is indeed actually 2. I did calculation to minus 2 epsilon. I thought, yeah, so that all the factors should be like this way. Yeah. Sorry, so that's, I need to make that correction. So let me repeat the calculation a little bit more carefully, what we have done last time. So for this one, so let's see. So the last time, so what we have done, so for next leading order is so this is we call sigma r, and this we call sigma v, sigma r and sigma v, and for sigma r is indeed, so the EE goes to QQ bar and G, and this can be understood as the follows. In fact, so the last time when we computed what we have done is that the yeah, we call it, this is P, momentum P, and here we call it Q1 and Q2, QQ bar, and the P gamma, sorry, yeah, I call it P gamma, but PG is okay, whichever. Let's go G maybe. Okay, so that's, we have calculated, and in fact, so if you try to compute this one, so this becomes like this way. This is B. So this is B, K2, I, E, gamma. So here I just take whatever. This is K1 and K2. Then GS times GS über GS. Sorry. And square, and unfortunately, there's no place to write down. It's super here. T, and then B. Sorry. So here you have QA. Q1, and then here Q2, and there's some color factor up here, color factor up here, TA, and also what you have is U bar A Q1 Q1, and then you have T A, and then Q2 slash plus PG slash plus M Q E E Q3. Okay, so this is the diagram for R, for sigma R. And of course, I call this one is L. So this one is L mu part, and then this part is M mu part. M mu part. So, and it's easy to compute that the L mu is equal to 1/4 sum of spin, or maybe I can just show up the so sum of spin of EE plus M or psi. So this is M R E minus E plus Q bar, and G the square is equal to you can just write down L mu 1 over P to the fourth H mu. So at the L mu is equal to 1 over fourth sum of spin V bar K2 times so you just take the complex conjugate of this L mu and sum of a spin. Okay, and then this is easy to perform the calculation. And it turns out that this one is K1 mu, K2 mu plus K2 mu, K1 mu minus K1 dot K2 G. That's easy to compute. However, this part, so the H mu uses M mu and mu star, and it has the information about this part. It has the information about this part, and which we got last time. By using dimensional relation scaled by factor of 2, but maybe it was trying to repeat the same calculation. In fact, here I didn't include the polarization vector of. In fact, you have to include the polarization vector of the gluon here. So, in fact, you have to include the polarization vector of gluon here, which I didn't. yeah, so here, in fact, you have to include polarization vector E slash, and here E slash. The polarization vector of the U. Yes. Yeah. So this E slash is the polarization vector group. Okay. Okay, so in fact, if you look at this part, you can just compare. So here, so you can just compare something like as follows. Here plus so this one is really just by using crossing symmetry. This is analogous to this E gamma to E gamma. So something like a quantum scattering. So where you have here, so what you have is this is Q1 and Q2 and then PG, Q2, Q1, and here you have P, similarly, one can have similar diagram here. You have, let's see, for instance, K prime, P prime, Kp. So this is just compound scattering, E minus plus E minus gamma goes to E minus gamma. So this is compound scattering we have computed. So you just bring this diagram to this way, this diagram to this way. Then what you get, you can just obtain the similar diagram here, right? Except here you have to use a gluon vertex instead of the photon vertex. So that's the difference only between them. Therefore, so one can use, so from here, here K prime, P prime, K and P. So you have S, so in this case, S is equal to K plus P square, and then minus time variable, K minus K prime square, and U goes to K minus P prime square. And when you go to this part, it becomes something like this way. So so S becomes T hat, which is P minus so here. So when you go from the compound scattering to what we are interested in, so P minus Q1 square is equal to Q2 plus PG square, which define T hat. Here you have S hat. Oh, sorry, U hat. U hat, which is P minus PG, which is Q1 plus Q2 square, and S hat. So this U becomes S hat, such that you have a P minus Q2, which is equal to Q1 plus PG. Okay, and then here what we have learned is this n square of E minus gamma square is what we already computed or you have computed in homework. S over U minus 2k square T divided by SU. Okay. so this is easily forced. So you can just replace STU by T hat, U hat, S hat. Now from here to here, there, so what we obtain is for M, that gamma goes to Q bar, G. Square is at the, here, what you get is NC, CF. Oh, and also there's the one correction last time. So last time I just write down CF is the trace of TA, but you have to include one of NC indeed. So therefore, in the case of QCD, this is the oh, I'm sorry. Yeah. So this is 4 over 3. Yeah. Times 4, and then Q square, E square, GS square, and S hat, T hat, plus T hat, S hat, plus 2 P square, U hat, and then S hat, and then U hat. Oh, I'm sorry, T hat. Okay, so that's what you obtain by just comparing these two diagrams and the replace Mandelstam variables. So that's how we obtain from one to the other. And in fact, so one can just rewrite everything in terms of the following variable. So I introduced last time. So xi is equal to 2ei divided by p. The p is absolute divided by p. Yeah. So the p is the p takes p000 as far as I remember the last time we have. So then this one becomes S hat T hat becomes P square 1 minus x2. This is P square 1 minus x1 and P square 1 minus x3. Becomes x3, and they just rewrite everything in terms of x1, x2, x3 here. And then what you get is indeed 24 CF, and then QQ square, E square, GS square, x1 square plus x2 square divided by 1 minus x1 and 1 minus x2. That's how we obtain this one. Yes, how we obtain. So you just have this factor into here, and then you just manipulate it. Bit of work. It's just like a 2-line work, and then you can show it. You can show it this one. Okay. So that's how we obtain, and then maybe I can erase here now. And then decay rate for d gamma. So decay rate, differential decay rate, gamma goes to QQ bar. G is in fact 1 over 2p and square Lorentz invariant phase space. And this Lorentz invariant phase space is indeed 2 pi to the fourth delta p minus q1 minus q2 minus pg. Okay, and then appropriate factor you would have d q1 2 pi q to e1 dq2 2 pi q. I mean, so x3 here is literally x0, whatever you call it. Anyway. To e2 dq dpg q 2 pi to the q 2e3. That's what I meant. Okay. And then it turns out so that writing it in everything in terms of x and y, x1 to x2, x3, and this is indeed becomes t square 1 to 8 pi cube dx1 and dx2. Okay, so now for total cross section, one can write down is indeed so total cross section one can write down for this sigma r is indeed sigma 0 alpha s over 2 pi cf 01 dx1 1 minus x1 x dx2 and x1 square plus x2 square divided by 1 minus x1, 1 minus x2. So that's how you obtain this sigma r. And once you use dimensional reduction, so this part becomes as follows. So once you use dimensional regularization. So once you use dimensional regularization, this is written in the Schwartz section 20. So then what you would obtain is let's use sigma 0 alpha s 2 pi cf 01 dx1 1 minus x1 over 1 dx2, and the integrand is 4 d minus 2 x1 square plus x2 square plus d minus 4 over 2 x3, actually x3 square, or I mean x3 or here you can call it or xg, whichever call it xg. Divided by 1 minus x1, 3 minus d over 2, 1 minus x2, 3 minus d over 2, and 1 minus x3, 2 minus d over 2. So that's how you obtain, but that's what you can get from dimensional realization. Okay? And then at the end of the day, so one can show up the last time I just made a mistake for the Eastern factor. So one can show up this sigma r is indeed equal to, so this r gamma naught rad gamma 0 sigma 0 for alpha s to pi, pi, and cf mu tail square d square 4 minus d 4 minus d, and I made a mistake about the lots of epsilon factor about epsilon square plus 13 over 12 epsilon minus 5 pi square divided by 24 plus 259,144 plus 4 the epsilon. That's how it is. So the last time I just made a shift, it goes to e goes to 2 over epsilon. Epsilon goes to 2 epsilon. So you need to correct it. And then that's sigma r, and sigma b cancel with these two divergent factor, and what you get is so what you obtain is indeed sigma next to linear order is sigma 0 plus sigma r plus sigma b, and what you obtain is gamma 0 grad sigma 0 1 plus 3 alpha s over 4 pi cf, and this is equal to grad gamma 0 sigma 0, and the cf is indeed 4 over 3. So therefore, it's 4 over 3 for QCD. Therefore, 1 plus alpha s over 4 pi. So that's a correction to next leading order. Oh, no, not 4 pi. 3 pi. Okay, so that's the next leading order. And in fact, so as I mentioned, so when you compare, so alpha s is around 0.11. If alpha s, that also depends on energy scale, and mu is around 90 GeV. So if you compute the alpha s structure constant for gluon coupling constant around the mass of the Z boson, the mass of Z boson, you get a 0.11. So it's a kind of small number. So you can just apply the perturbation theory. And this is a correction. So this correction would be around 0.035. So this is around the 0.035 correction to the 1 plus 0.035. So it's a perturbative corrections. That's the correction I want to make. So last time I just write down 4 epsilon square, and this is 24 epsilon. But so the dimensional relation here is indeed the usual convention. Last time I just put 2 here, so I'm very sorry. Okay. And another correction I want to make is, let me erase everything like this. So convention I just write down. So the K prime E, and then so and so last time I just write down this is Q is equal to K prime minus K, but I just want to change the opposite. This is more natural convention, K prime. And here, so today I'm going to call this CP. This is momentum CP. So this is called longitudinal fraction. I mean, if you open the task controller, it's called C is longitudinal fraction. So the quark, so this is quark, and C P plus Q. I mean, I don't want to use Q because Q for quark, because I always use Q for momentum. So this is momentum. Cp plus Q is a momentum. And then, so therefore, the Y last time I used is Q dot P, K dot P is indeed K minus EK prime. Okay, that's the correction I want to make. Okay, and also B is P dot Q. This is M EK plus EK prime. Okay, that's the correction I want to make. And then, so where we are. So last time, so we start talking about this. So deep inelastic scattering. Okay. And then if you bump E to the electron to the proton or neutron or nuclei, this is proton, and very high energy, then one can just, of course, there is something going on here. So you can just resolve inside of the proton so that some quark pop out with some fraction of the momentum is taken away from the proton. Okay? Then there is some QED process occurs. So because they just interact with the photon gamma. Okay? So this quark interacts with the high energy electron via photons. And then, so we will consider so-called Parton model today, and then which is the end of today's discourse. Okay. Any questions so far? I hope people are listening. You guys requested to give a lecture, so you should listen at least to today's lecture. Okay. That's what we're going to think. Again, we're going to do the same thing. Yeah. So let's review a little bit. D sigma, D omega, D E prime, this log scale is indeed alpha E squared divided by 4 pi. Just a bit of review. This proton Q to the force E prime over E L mu W mu. And L mu really come from here, and W mu really come from here. Or the last time we didn't look at like this way, so we just look at the like this way. The last time is just Q and so on. So that last time, so we just look at this process, and the Q really come from here. So sorry, W mu really come from here. Okay, and then so this is called leptonic tensor. It's called leptonic tensor. And this is hadron. Hadronic tensor. Hadronic tensor, and then so this L mu is easy to obtain, which is trace K slash gamma mu, K slash gamma mu. Okay, Parton slash. So this is the one we obtain, we can obtain. From this leptonic, so this part is easy because I mean it's the same as what I have written in before, just 10 or 20 minutes ago. And also the hadronic tensor is just by using word identity, word Takashi identity, one can just determine the form of the plus W2 P mu plus P dot Q divided by Q squared Q mu. This is a minus sign. P mu minus P dot Q squared Q mu. Okay. So let's see the hadronic tensor should be, because we just added the word identity is 0, and also the W mu should be symmetric. Then from here, one can obtain from here, so one can just obtain the plug this one into here. Then what you get is as follows. I can just write down here. So I can just write down. So this is equal to for E squared so this is the result one can obtain. But the last time I just write down the different way. So the last time the sigma square, I use this notation 4 pi x alpha E square q square q square x square xy w maybe y square w1 plus 1 minus y q square, and here b w2 over x. That's what I have written last time. But it's the same thing. So the last time I just write down like this way. Like this way, but one can just rewrite everything in terms of d omega d prime instead of dx dq square. Okay. And you will obtain this one. And then so it's called the Buchan scaling that so when you take if you define f1 is equal to w1 over x and f2 is b w2 x, okay, b w2 over x, then these are called structure functions, because it knows about what's happening it knows about structural problem. Okay, and this f1, f2, and then behave know about Buchan scaling. So when you take the limit q square goes to infinity, b square, b goes to infinity, yeah, I mean, here this is b, and this is also b. Then b is defined here. So when you take b goes to infinity, then you have x is equal to q square to be fixed. So this is this kind of double, it's called double scale limit. Then f1 so this will be this is going to be Buchan scaling. Okay, so this behavior is called Buchan scaling, and I'm going to explain how this Buchan scaling can be explained by using the Parton model. Okay, Parton model is written here, so I'm going to erase this part. Okay. So okay, so Parton model is literally consider that the proton. So if you just inject the high energy electron to the proton, you just bump in the proton and electron. If it is high energy, the energy high enough, some quarks pop out with certain fraction of the momentum and interact with the photons. Okay, that is a very simple process. We can just consider. And then, so now for this sigma of E minus the proton minus the proton and E minus of some hadron, X is some hadron, is given by a sum of I and 0, 1, dc I. So if I c, this c is called longitudinal fraction. I don't know why it's called longitudinal fraction, but that's how people call it. And the sigma hat e minus and pi goes to e minus x. So if I is so this pi is called Parton. Pi is a Parton. And I call it quark or a quark, but it can be gluon. Sorry, so it can be quark or gluon. And if it is a case of gluon, you have to anyway. I will explain. So Parton is just a quark and gluon indeed. Okay. Here, so this part is really this Parton pi. I mean, there are too many p and too many q and so on. So I'm very sorry about it, but that's the physicists use notation. So you have to distinguish from the context. You have to distinguish from context. If pi is quark, then it's easy to evaluate. This process. If it is quark, this is just QE process. It's a EE to mu, right? And you can use EE to mu formula. And in fact, so it's very easy to compute this part for if pi is quark, and then d sigma hat d omega dE prime. If this is quark, E minus Q. This Q is quark, not the momentum. So you have to distinguish by context. Okay. Unfortunately, that's how physicists mix up notation. If you're a mathematician, don't do that. And physicists are really sloppy about the sloppy and they mix up all the notation, which I'm not impressed so much. But unfortunately, that's a convention in the physical literature. So this is alpha E square E QI square QI square. So QI is the fractional charge of this quark. And then for E square sine for theta 2. So sorry, theta is here. Theta, I didn't explain what theta means. You have to ask me. You have to ask me. Theta is here. Theta is this direction. This okay. That's the theta. Theta, and then so cos square theta over 2 plus q square 2 and q square and sine square theta over 2. And of course, you have the energy conservation. And in fact, so this okay, so that's the one can obtain. So this formula is particularly called I think there's a name for it. I mean, you have learned it in QFT1. What is it called? I already forgot. Oh yeah. So this formula is called Rosen. So this is called Lorenz formula, and then if you search Lorenz formula in Peskin Shredder, you can find it in the material QFT1. So it's easy to compute. So it's a good exercise to do if you are interested. Okay, that's the formula you obtain. And then let's manipulate a little bit more this formula and plug that one into here. Okay. And this one, delta function, delta E minus E prime minus Q squared 2MQ squared is indeed equal to delta Q squared 2MQ x minus Q squared 2MP, sorry, no, MP, C. Okay. So here, what I use is E minus E prime is equal to B over MP, which is equal to Q squared divided by 2MPX. Okay. So that's the formula I use to plug that one into here. What you obtain is this formula. So MQ is equal to MP times C, because you just pick quark mass is the just obtain the just fraction of C, multiply fraction of C times mass of proton. That's why you get this one. And this is indeed equal to 2MP over Q squared delta, X squared delta C minus X. So you just use the standard formula for the delta function. And then just use delta function for using this one and plug one back into here. Plug that one to here, and then what you get is this is equal to, let me erase this part, and this is equal to sum of fi x alpha e squared qi squared divided by 4e squared sine 4 z over 2 2np q squared x squared cos squared z over 2 plus 1 over np sine squared z over 2. Then now one can compare between them, and then one can conclude that the maybe I can erase some part. One can conclude that the this W1 is equal to 2 pi sum of qi squared fi of x, and W2 x cubed x cubed, which is equal to 8 pi x squared q squared sum of qi squared fix. So here, as you can easily see, here fi is a probability. So this is probability Parton probability. It's called, I already forgot, it's called Parton, okay, sorry. So this is called, so this Fi is called Parton distribution function, Parton distribution function. So the DXC Fix is the probability such that the Pi will pop out with momentum c times p when you inject the electron to proton, okay, to proton. Then it's a probability to get a Pi with this momentum. So this is a probability function. And then, so this W1 and W2 written here can be written in terms of this probability function, P, Parton distribution function. So this is Parton distribution function. Okay. If you use this Parton model. So therefore, it's easy to see that this W2, W1 of xq is related to q square divided by 4x square W2 xq. By just looking at the Parton model, okay? The formula coming from Parton model. So then, of course, just plug that one into. So this is x, just x. Plug this one into here. What we obtain is that it's called for column. So this implies that this is equal to F2 is equal to 2x F1. Okay, so that's you can obtain from the. So therefore, these are called. So this relation is called. This relation is called Cullen-Gross. This relation is called Cullen-Gross relation. Okay, let's see how we obtain. So and also, yeah, that's Cullen-Gross relation. Of course, when you take this limit, when you take this one. Any questions so far? So that's how explain the this Buchan scaling by using Parton model. Any question so far? Let's see. So if you use this kind of Gross relation, one can just rewrite this relation, this formula in a different way, like this way. Maybe I can just erase some part. Maybe I can erase this part. So one can just show that this dE prime d omega can be written in terms of 2mp E divided by E prime so dx dy x and y I already introduced before. then this d sigma to by alpha square q to the fourth s 1 plus 1 minus y square, and then so just plug this one, plug this one into here, and then here you can just write down sum of qi square fi of x. Okay, so that's how you obtain how we can just rewrite this scattering as the cross section, differential cross section in terms of y and x. Okay, so that's a good exercise to do, so I can just show you if you're interested. Any questions so far? So what's important here is just that what we have done is very, very simple thing. You just replace the proton to the, inside the proton there's some Parton inside here. And the Parton, to get out of the Parton, to get Parton out of proton is the probability is dxc fic, okay? And just sum over everything, sum over all Parton, which is co-congruent. Okay? And then one can just explain this in the Bjoken scale. That's what Feynman did to explain this Bjoken scale. Okay. And as you know, the proton is made of quark, which is UUD. So therefore, what you would expect is that this Parton distribution function has the following properties. So for proton case, so the FUC minus FU bar, so this anti-up quark, is of course is an average for 2 dxc, because you have a 2 up quark. And if you do the down quark, the same thing for this anti-down quark. And the probability is 1 because you have 1. And the rest of the quark, F quark for rest, minus F quark is 0 otherwise. Yeah, Q is otherwise. Q is otherwise, and also you have to include the momentum conservation. Sum of I dxc fic, and also you have to multiply c is equal to 1. Okay. Now if you just put the p inside here, okay, p inside here, you get the p. So this is momentum conservation. This is oops. So this is momentum conservation. And here is more like a flavor conservation. Okay. Okay, so let's see. And in particular, some notation of this. So these are called, these two quarks are called, U and D are called, these are called balance quark. Balance quark. And the other quark is called C quark, I think. Yeah, C quark. Okay, so let's see. let's see. Yeah. The property of this Parton distribution functions. And then, of course, what we have done is just tree-level calculation, and what we can do is the next leading order. Okay. So what we have done is this leading order, and then if you want to see the quantum effect, then you have to go to the next leading order. That's what we are going to do. Any questions so far? Okay. I think it's a good place to take a break. After 10 minutes, we will resume. If you have a question, just tell me via WeChat. Hopefully you are listening because you requested me to give lectures today. Otherwise I wouldn't. So which song? Which last piano? Which one do you want to listen? Last piano. I didn't decide which one I should turn. Okay, let's resume. So the question is, just a moment. So what was the question? The question was, so since, what was it? So since this pi has a momentum, so this so E has a momentum K, pi has a Cp, okay? And this cross-section should depend on C, well, true, but here, I didn't write that explicitly, but here just take log scale, log frame, and I just take a log frame, so that the proton is at the rest. Therefore, here, only place that enter in C is the mass of the quark. Mass of quark is C mass of proton. C mass of proton. Because we take the rest frame of proton. And then, so I already erased, and at the end of the day, so this delta function will give you C minus X, essentially. The rest of the part is independent of C, so you just replace C by X, then you get this. You get this part. Does it answer the question? Does it answer the question? Are you listening? It seems like you're not listening. Or are you taking rest? Still rest. Okay, I hope. So it is related to momentum conservation. Yes. So the only place that I'll enter is really, so the MQ is here. So now for this you can just have P square. And also the other function will give you this function is this energy conservation or momentum conservation, whatever you call it. Will give you, after change of variable, you get the some factor times delta c minus x. And when you once you include this one into here, I mean the dx integral essentially c is the other function. You just replace c by x. That's what happened. Yeah. You just replace c is equal to x. That's it. I mean, this is very natural. I mean, why did you? Okay, so let me explain to you. This is very natural that for instance, yeah, I mean, for instance, so if you look at this process, essentially what you will get is Cp mu plus Q mu is this is the final, right? This is, let's call this P final, mu. And if you square it, what you will get is m square q plus 2 pi. So this is pi, of course, pi mu. Pi dot q plus q square. If you just square it, and here you get the mq square. So from here, you just obtain q square is divided by 2, pi dot q is equal to 1. Okay? That's how you obtain. And then by definition, from here, you get x is equal to cq square divided by 2 pi dot q, which is equal to c. So now for x, the c is replaced by x is very natural. By energy conservation. Yeah. By energy conservation, yeah. Okay, so let's move on. So this is tree-level calculation. What we are going to do is the next thing in order, and then we're going to erase everything. Okay, so what we can consider as follows. So next leading order. From, so what we are going to do is so-called, what is it called? I already forgot. So it's called, so the DGLAP, which stands for Doc sheets. I'm sorry, I think they were Russians, I guess. Just please search Wikipedia. Krylov. Libatov. And I think the Italian. Actually, I look at the paper arbitrarily and Parasi original paper. It's very well written. I mean, I think it's written 1970 something, late 70s. But I thought it's hard to read, but it's very well written. I mean, you can read actually, even though it's lots of gap in years. It's almost like a decades ago. Oh, no, few decades ago. But it's still readable. It's kind of very well written. I mean, that's how the paper. It's a typical example. That's how paper should be written. So maybe good idea to take a look at it. And I also recommend you. I forgot to tell you. So that after this talk, this course, it's better to read the Weinberg's theory of leptons. It's a 4 pages paper, super well written. You should read. I will send you via WeChat. So that's what we are going to do. And the process we are considering follows. So the So these are next to the other, so it's very familiar, right? You already computed this one. We already computed. And then, but however, there are also diagram, something like this one. So here, proton emit the quark, and there is a gluon emission also occurs in between. So here is just gluon emission absorption, but here the proton emits the gluon first, and the gluon just decays the quark. Yeah. So these are 5 diagrams that contribute to the next leading order for this process. But what we are interested in, so these processes, so I'm going to explain what it means, but these processes will give you, this is called, it's called splitting function. So these 3 will give you so-called P, QQ splitting function. I'm going to explain what it is. Function. And these 2 will give you PGQ. splitting functions. Since the PQQ is the simplest and we already essentially compute this diagram, so I'm going to compute PQQ. I hope my handwriting is good enough to distinguish Q and G. And this is G. I'm sorry. I think I told you wrong. And somehow, sorry. I think I got confused about notation. Maybe this is called PQG. I don't know why. Why are they called PQG? I thought PGQ. Okay, let's leave it as it is. I hope I'm correct. Okay, so let's divide this three diagrams first. Okay. Okay, so essentially we already computed so we already computed EE to QQG and QQ bar G and also this diagram. So it's the same calculation what we are going to do. So and everything done in actually Schwartz, and the calculation is really correct. Schwartz section 20 and section 32 for dimensional realization. And then also you can just take a look at the paper by Terry Paris's paper, the original paper. I mean it's the same. So actually the arithmetic Paris's paper, they take this way of regularization. That's why I made a mistake. I just look at this original paper and then they use 2 epsilon notation. That's why I made a mistake last time. D is equal for if minus 1. Okay, dimensional regularization. And again, first you can evaluate this one by dimensional regularization. So what we are going to do is the W mu. This is Parton. So here again, so you have L mu. Sorry, from here you get the L mu. So lepton tensor from here you get the Parton tensor. So this is L mu is very easy part. We already know this form. So we are going to evaluate the W mu, which takes the following form: sum of I 0, 1 dc 0, 1 dc f I. So this is Parton function W hat mu zq delta x minus c. Wait, what is z? So z is the fraction of the z can be defined as follows: q squared. So the z is this part. Z is this 2 pi of q. So this is the counterpart of Partonic version. So Partonic version of x. of course, it's already in next leading order. So therefore, it's not that simple. So here, this is not 1, no longer 1. Okay. So you have to replace it by z. Okay. And z times c will give you x. Okay. That's the energy conservation. One can just use. And then what we are going to evaluate is indeed, so that one can just perform the integrals of the so one can perform the integral first, and so that you can just reduce everything in terms of integral of c. Okay, and then what we are interested in is for simplicity, we just take a contraction with for simplicity, so we just take a contraction between G mu nu. W mu hat. And let's call this is W0 hat. And then, so from here, we call this one is again the similar notation W0V, W0B, and W hat 0 hat. And then from these two, you get the W hat R0. Okay, that's a notation we are going to use. And then all the computation done in Schwartz and section 20 and section 30, and essentially we have done briefly, even though it's very disorganized manner last time. Let me, okay, maybe I write it down here. So here, W0 hat B can be written as follows: 4 pi qi squared 2 pi cf 2 pi squared mu squared divided by q squared. Actually, this computation is exactly done by this original paper. I was surprised. It's so well written. Gamma 1 minus e over 2 divided by gamma 1 minus epsilon, and then minus 8e squared minus 6 over epsilon minus 8 minus pi squared over 3 times delta 1 minus c. So that's W0B, one can evaluate, and then so W0R is also can be evaluated as the same manner. It's the same computation, and what we will get is 4 pi qi squared of s over 2 pi cf 4 pi mu squared q squared epsilon over 2 1 minus epsilon over 2 gamma minus 1 minus epsilon and 3z plus z e over 2 1 minus c minus epsilon over 2. Oh gosh, it's a long calculation. It's c squared 1 minus c plus 3 minus c minus 3 over 2 1 minus c minus 7 over 4 epsilon 1 minus c. And then we would like to see the cancellation of the pole here and there. Here it's one over epsilon squared and this one here. And to see the cancellation, we need to introduce so-called some special notation for some function. I'm going to introduce the following notations. So 1 plus c plus. So this is, I don't know how they introduce this notation. Sorry. So 1 minus c is equal to z when z is less than 1. When z is less than 1, this function, this plus sign, is equal to 1 over 1 minus c. But of course, when z equal to 1, that's something, it has a problem. So that I have to treat it very carefully. That for instance, this plus sign is indeed the same as 0, 1 dx f of x minus f of 1 divided by 1 minus x. Okay. Now, of course, when integral from 0 to 1 minus epsilon, everything is the same. So you don't need to worry about this one. Okay. However, this, I don't know how they find this, how they introduce this plus function. It's called plus function. When z is less than 1, this is the same, but when x is equal to 1 case, you have to take the difference between. So the 1 minus x will cancel the denominator here in somewhere. If you introduce this plus function, indeed, so this w0r can be written as follows. There are lots of ways. Even Pascal and Schroeder has written in some way, and also here 1 minus z 1 plus epsilon can be written as follows: 1 minus epsilon delta delta c plus this plus function minus epsilon. Plus sum of n is equal to 1, infinity minus epsilon over n and factorial log n 1 minus c 1 minus c and plus function or plus function. Okay. I'm not going to explain what's this. It's not relevant, so I'm not going to explain what this plus function, even log include the log. You can define it in a similar way. Because it's not going to play any important role here, so I'm going to skip. If you're interested, you can just take a look at the Pascal and Schroeder or Schwartz, whichever you want. I don't know how they obtain, to be honest, how they introduce this plus function. Don't ask me. Or just tell me, please search in the literature why particle physicists introduced this plus function. And this one, using plus function, one can just write down as follows. So you can what we want is just to cancel one with e squared term here, with here. So to do that, they somehow introduce plus function. If there's a homework, if there was homework, I would give you as an exercise and homework. But unfortunately, you don't. So no homework, but it's good exercise to do. For s over 2 pi CF, it's super tedious calculation. And times, it's super tedious calculation, 3 plus 2z minus 1 plus c squared 1 minus c log c plus 8 epsilon squared. So you just apply, so this calculation, you just apply this calculation into 1 minus z minus epsilon over 2 and then this one, and also this one, and this one. Then what you get is 8 over epsilon squared and plus 3 over epsilon plus 7 over 2 delta 1 minus c. Okay. So you just apply, so this 1 minus c minus epsilon over 2, and you just look at the denominator and apply this formula. And you get this contribution. And that will give you this 8 over epsilon squared term. It's a super tedious, one can do that, but if you're interested, you can do that. There's no homework anymore, so if you're lazy enough, you can just leave. 1 minus 1 minus c plus and so on. It's not an important term for log term, so I'm not gonna write down everything. Okay, so that's how I obtain. And so this 8 over epsilon squared cancels with this one. Okay. And then let's write down everything in the put everything together. Put all together. Okay. So then, so this W0 hat is W0 leading order, which we already evaluated, plus W0 B hat W0 R hat is given by as follows: 4 pi Qi squared minus c 1 over epsilon of s pi pqq, so pqq z. So this is the splitting function I'm going to write down later. And 4 pi mu squared, super tedious calculation actually. 2 gamma 1 minus epsilon over 2 gamma 1 minus epsilon. Plus, blah, blah, blah. It's super tedious, I'm not going to write down everything. You can just look at the Schwartz paper, Schwartz calculation. And then, dot, dot, dot. And what's important is this distribution is known, this P, this splitting functions. Splitting function, this is equal to CF 1 plus z squared 1 minus 1 minus c plus 3 over 2 delta 1 minus c. Okay, so that's how it obtains. How we can just write down, just sum these R and the B and cancel this one, and only look at the 1 over epsilon term, 1 over epsilon term to read off this QQ splitting function. And then So this single pole is in the Parton cross section is not a problem. If the calculation dropped out of the physical prediction, so that you just plug this one into, I already erased here, plug this one into the original formula, and what you will obtain is follows. I mean, super tedious calculation. I mean, unless you really want, I mean, you will see how tedious the calculation is if you follow the calculation. I really don't want to do that again. Don't want to do it again. So plug the original one. So this original one is W mu nu xq x1 dx of c fi of c and W mu dot x of c over q. So this is the original formula, and you just contract with minus g mu nu and minus g mu nu here, and this becomes W0 hat, and plug that one into here, and then you will get is W0 xq is equal to 4 pi sum of qi square x1 dc c fi c c, because z is equal to x over c minus of s divided by 2 pi and splitting function, QQ splitting functions. X over c and plus log mu Taylor square q square and plus finite. The super tedious calculation. After you do the super tedious calculation around here. Okay. So then. So you just look at the difference between at the certain energy scale with the energy Q. But okay, so almost there. So you just look at W0 xq and difference between some certain energy Q0, certain energy Q0. And then this will just, the infinite part that will disappear, qi square x1 dc c, oh no, sorry, fxc alpha s over 2 pi p qq, and then x over c log q square q0 square. And this is final result. Okay, so once you know about the information at the W0 at a certain energy level, so you know that you only just want to measure difference between them at the different energy level Q. That is fine. Okay, so that's the formula one can obtain by just looking at the next leading order calculation, and so and everything is here. Oh, I'm sorry. I think I miss. Oh, I'm sorry. So this is 2 over epsilon. Sorry, 2 over epsilon is missing. Somebody should tell me, or you guys just listening. Sorry. So please add 2 over epsilon here. Okay, I'm sorry. I didn't include this one. And so 2 over epsilon just cancel between them, and what's left is this log dependence of energy scale. Good, almost there. And then, so what we have calculated as follows. So in fact, one can just use the RG notation of the so this will give you the renormalization group flow for this Partonic tensors. This Partonic tensor W0. So this W0 is the depends on energy scale, which can be written as follows. So at a certain energy scale, tree level, you just write down a tree level calculation. You can just write down like this way: x mu is equal to q, tree level, and then so this equation will tell you as follows. So this equation will tell you that the f of x and mu1. So this fi. Fi is a Parton distribution function, and at tree level, so the W0 can be written like this way. Okay, maybe should I show that at the tree level? Maybe let me show. I think I just skipped one step. So let me show this one first. So let me show this one first. I skipped one step. So W0 is minus G mu nu, and this is equal to 3W1 xq minus W2 xq and MP square plus Q square for x square. So you just use W mu. The form of W mu is W1 plus W2 factor, right? So I've already write down this one in the previous this lecture and the previous lecture. So minus G mu Q mu. So this is determined. These here factors are determined by Ward Takashi. That's already I told you. And then you contract the G mu, you get this one. That's a simple calculation. And then once you take Q goes to really large limit, so it's a deep inelastic scattering limit. So this is equal to indeed 3W1 minus Q square 4x square, and then W2, and you use Colin-Gross relation. So that the Colin-Gross relation, so that this is equal to 2W1. Okay? Therefore, this is equal to W1 is already written somewhere in the 1 hour ago. Almost 1 hour ago, it's equal to 4 pi sum of Qi square Fi x at the tree level. So W1 is this one, right? 2 pi times then times 2. You get the 4 pi. This one times this one. And the tree level, this one is the case. And at certain level, it's a really high energy. It's a QED has asymptotic freedom. If you go to really high energy, you can just fill up potential is really bad. But if you change the energy to lower, you have to include all those next leading order corrections by quantum effect. And this formula indeed encodes how this F, the Parton distribution function, depends on the energy by this renormalization group philosophy. So, in fact, using this plug that one into here, what you will get is the Fi x certain level mu1 is equal to Fi x mu2, and the mixing occurs plus alpha s over 2 pi 1 over x dc c Fi c mu PQQ C x over C. So this is mu1. mu1. And this is still, I don't need to call mu. So mu, and the log dependence, log mu1 square and mu. Okay? So plug this one into here. Okay? You can just show this is the relation. So now for the tangent derivative with this scheme here, you obtain finally this what is called DGLAP equation. Then this is the final step. And then mu Okay, so this is called DGLAP equation. You just take a derivative with log mu. So you just get rid of this log mu derivative, and you get this part. Thank you. So therefore, Parton distribution function F really depends on the energy scale you measure, and this energy scale dependence can be read off from this DGLAP equation where the PQQ is splitting function, which is written over just 20 minutes ago. And if you use this where PQQ, let me write down again. Z is equal to CF 1 plus C square 1 minus Z super TX calculation, you get this as 3 over 2 delta 1 minus C. And what's more important is that if you use the definition of this plus function, you can just show that the conservation of is equal to 0. Okay, so that's how this splitting function really encodes the energy dependence of the Parton distribution function. And then furthermore, one can just consider there's a so-called operator mixing. That is the operator mixing. Anyway, you can generalize this DGLAP equation as follows. So in the two diagram I already raised, so that this one sometimes pop up the gluon and then it scatter the quark and so on. So this diagram I already erased, and also I just erased the diagram, something like that. Like this one, right? And from here, so one has to use FG, so of X. So this is Parton distribution function for gluon, okay? Even though it's the proton is made out of proton is UUD, but they are bound by the gluons. So therefore, if you smash electron onto the proton, there is a probability that the gluon will pop up. So that probability will be measured by this gluon distribution function. And then if you do the computation for similar computation for I think what I have written is correct. Similar computation, you will get the mixing of Fi from X, Fg from X, so it becomes vector, so that the everything is mixed up. Sum of j over pi x goes to 1 xc over c and then splitting functions. There are lots of splitting functions. P Q I Q J P G Q J P Q I G P G G and F J and then F G. It's a Parton distribution function, and xc and here, xc and here. X over c. Okay, so if you consider, in fact, to be more precise, you need to include this diagram to read off these splitting functions. You have to consider all the process, and then everything Fi and Fg are mixed by these splitting function. But essentially, it's just this renormalization group code is encoded by this DGLAP, this vector value or matrix, and it's mixed by matrix of the splitting function. That's the final formula. And then this splitting function just can be evaluated by this loop, like a loop diagram or next leading order diagram. That's how you see how this Parton distribution function depends on the scale. I think I should use mu here. The energy scale you measure. And this DGLAP equation plays a very important role in the analysis of LIC at CERN, and that is now at rest, but it's running for 10 years. It has run for 10 years, almost 10 years. And this DGLAP equation plays very, very important role for analysis of latency. Okay, so that's all for the QFT course for 1 year. I'm so super exhausted, as you can easily see. Any questions? But I think we covered a fairly good amount of material. And then if you follow my lecture, even though I made a lot of mistakes in the middle, you must have learned a lot. And I'm very exhausted. Any questions? I'm super exhausted. So that's all. Yeah, that's the end of this course. So now, teaching assistant is creating solution 6, and after we will grade after that. The homework 6 will be graded after that, and then also, after that we will determine the grade of your this course. And I heard this is not a mandatory course, so I try to be easy on you about grading, about your grade. So there are no Q&A session. So just if you have this week, this is all. I just want to take rest from this, take a distance from this lecture. So there are no Q&A session this week. If you have questions, just contact me directly. And we will grade homework 6 soon. What else? Do you have any other questions? No exam? Okay, that's it. So if you want to join the dinner tonight, let's meet downstairs at the 6 p.m. I'm not gonna wait you, and we will go to Yohan. Over there, you can pick restaurant, whatever you would like to eat. And then, yeah. So if you want to join the dinner, just let's meet at the 6 p.m. downstairs. Okay, see you. Thanks for taking my course for 1 year. Bye bye.